Okay, here's one more short little video, hopefully, right? This is our problem that we talked about the other day at the end of class, right? So I'm going to let you do that, right? Do that for yourselves. What is the solution of this initial value problem? Y prime is y squared, y of 0 is y naught. Okay, so spoiler alert, we're about to talk about it. So you should just turn this off if you want to just do it all on your own. Okay, so let's, since we've been talking about t as an independent variable, let's rewrite this guy. If I was going to solve this guy, I would write it as dy dt, right? I'd write it in this notation, is equal to y squared. Yes? Okay, very nice. And now I'll just let you go through the steps of showing that y as a function of t is equal to minus 1 over t plus a constant. Okay? So you should fill in those steps. All right. Now let's apply the initial condition, right? Y at time 0 is some unknown initial condition. Why not? Just leave it be, anything. And so what do we have? Y evaluated at 0, right? Over here is minus 1 over c, right? But we want that to be y naught, right? So what is c? C is just minus 1 over y naught, right? Okay. And so since c is minus 1 over y naught, then we can put that in here. Minus 1 over y naught. Yeah, then we got a lot of minuses. So if you multiply everything by a minus, then we just get that. One way to write the solution of this ODE is y of t is equal to positive 1, which multiply everything by positive 1 over, so we'll have 1 over, or multiply everything by a negative, 1 over y naught minus t, right? Negative, negative, and that negative. Yes? Okay. All right. Now notice our original solution over here where we said y of t was minus 1 over t plus c is not a general solution, right? Why? Think about that. Why is that not a general solution? It's missing a solution, right? What's the solution of this differential equation? It's not included in there. Well, let you think about that. All right. So let's just look at this, though, for a sec. So this is more interesting than it looks, right? What does this say? This says the rate of change of y with respect to time is equal to twice y itself, right? Or sorry, y, not twice y itself, y times itself, right? Okay, y times itself, y itself squared. All right, as a f of x and y right-hand side, we talked about this, completely continuous, partial f, partial y, 2y, completely continuous everywhere. We wouldn't expect crazy things to happen, right? But what do we see from this, right? You know, we have blow up at t equals 1 over y naught, right? Okay, so what does that look like, right? If y naught were equal to 1, right? So if y naught is 1, then I'm just solving y of 0 is 1 for the initial condition, right? Then what is y of t? Y of t is just simply 1 over 1 minus t, yeah? 1 over 1 minus t. Okay, and what happens, right? Here's the t-axis, here's the y-axis, yeah? And when t is equal to 1, right? What happens? T starts at 0, right? What is y of 0? Y of 0 is 1, yeah? Y evaluated at 0 is 1, yes? Okay, so if we're in that case, y of 0 is 1, that's our y naught, yeah? And then what does that solution do? Well, what is the limit as t approaches 1 from the left of y of t? The limit, you know, as t approaches 1 from the left, right, time is increasing from 0, right? As t gets close to 1, what happens to this guy? As t gets close to 1, we're getting 1 over 0, right? This is going off to infinity, which does not exist, right? Okay, so what happens, right? We just have this blow up, right? Blow up when t is 1. okay? So we can generalize that to any y naught. Blow up occurs when t is 1 over y naught, okay? So if y naught is 10, blow up occurs 1/10, right? If you're measuring in seconds, 1/10 of a second, that's not so good, right? For whatever it is you're modeling to blow up, yeah? Right? What if this is saying, you know, what if y is the, you know, the largest magnitude of a vibration in a launching rocket, right? And you're like, oh, it's just a tiny vibration. You know, maybe it's like a, you know, maybe the initial vibration, the largest magnitude is 1/100th, maybe. But if y naught is 1/100th, right, then that's going to say blow up occurs when t equals 100 seconds. And if you need more than 100 seconds for your rocket to get past that stage, well, that's not good. By the way, there is a Mars rover landing on Mars today at 3:55 p.m. NASA TV. All right, let's see, what else did I want to mention? This was just a fun thing to think about. Fun in that it's super unexpected. Hopefully you kind of thought about it a little bit yourself, and it's the difference between a linear solution and a linear ODE and a nonlinear ODE. If this were a linear ODE, like y prime equals y instead of y prime equals y squared, we know this is an exponential growth solution, right? Yeah, as t goes to infinity, solutions grow unbounded, but there's no unbounded growth for any particular value of t, right? E to the t. Yeah. So that's it in a nutshell about a nice, simple little way of thinking about the difference between nonlinear ODEs and linear ODEs. Of course, this guy, we could also have used instead of solving, we could also have used our methods to think about the phase portrait, right? And if I did that, just to reinforce a little bit, right? What is the equilibrium solution for this guy? Yeah, y equals constant, so that's the y prime, which makes y prime 0. Good, y equals 0. Our solution that is not contained in this solution, right? Y equals 0. There's no value of c that's going to make that solution 0, right? Okay, so we've got equilibrium solution of y equals 0, right? So we know we got that guy here, yeah? So this is our t-axis and this is our y-axis, and here's our y equals 0, which splits the plane into 2 regions, right? Where are solutions increasing? Well, y squared is always positive, right? So it's increasing for both y positive and y negative, right? Because we have 2 regions. Y positive we're increasing, y negative we're increasing. But we cannot cross the equilibrium solution, right? And so, because this guy satisfies Picard's theorem, right? Okay. And so, then what about concavity? This is what tripped many of you up on the quiz. Concavity, I need y double prime, right? Y double prime means take the derivative of y prime, but this is the derivative with respect to t, right? Remember, this y squared means y of t squared, and this y prime means derivative of y with respect to t. And this y double prime means second derivative of y with respect to t. And so if I take the derivative of both sides with respect to t, right? This side is d squared y dt squared, which is y double prime, and this side is the derivative with respect to t of stuff that depends on t squared. And what is the derivative of stuff that depends on t squared? 2 times the stuff times the derivative of the stuff, right? So what is y double prime? And most of you forgot to do that. 2y times y prime. Well, what was y prime? Remember, y prime was y squared for us. Y prime is y squared, 2y squared, that's 2y cubed, yeah? Okay, and 2y cubed, what do we know, right? If we're talking about concavity, right, then this guy's going to be concave up when y is positive, because 2y cubed will be positive, and concave down when y is negative, because y cubed will be negative, so 2y cubed negative, right? And so this is increasing concave up here, and increasing in concave down there. And so solutions off of equilibrium are increasing concave up, right? Which we kind of see, right, from our specific solution, yeah? Okay, it should not go up, right? You get that, okay? Yeah, right? Right? But there's no real, whoops, they don't cross, right? We know that too. So there's no real reason, right, from this phase plane analysis idea to have expected this blow up in finite time, though, that we can see from having done the solution. Yeah, does that make sense? And then down here, right, it would be increasing concave down. And so there, increasing concave down, right, not everything is nice as long as our initial condition is negative, right? If our initial condition is negative, then what's going to happen long term? Long term, our solution is going to go to 0. Y is going to go to 0. If we start with an initial condition, right, where y naught is negative. Does that make sense? And that's another super nice way to think about these problems. We're going to take another look at equations like this in a little bit and look at yet another adaptation of the phase diagram ideas. But again, not all complex behavior can be captured from that, right? Which is kind of one of the things we saw here. Alrighty, that's all. I will see you next week. Have a nice snow week.